Welcome to Module 5, where we'll be discussing the logic of conditionals. We'll be covering the content of Chapter 7 and most of Chapter 8. However, we'll leave the soundness theorem from Chapter 8 for Module number 6. So this week we've got 3 learning objectives. The first is to show that a collection of connectives are truth-functionally complete. We'll first show that the collection consisting of conjunction, disjunction, and negation is truth-functionally complete, and we'll give a pretty systematic argument for that. But then we'll use that fact, or we'll sort of leverage that fact to prove that other collections of connectives are also what we call truth-functionally complete. And really what that means is that all the other truth-functional connectives can sort of be built up or constructed from that collection of connectives. So we'll talk a little bit about that and how to go through something along those lines. We'll talk a little bit about translating conditional statements from English to first-order logic. And a conditional statement is a statement like a if-then statement. But in the English language, we have a lot of different ways of saying if-then, and so we'll be discussing a few of those. And then finally, probably the most important part of this module and this particular set of learning objectives is being able to construct formal proofs using the elimination and introduction rules for the conditional. And we'll not only introduce a connective for the conditional, but also for the biconditional as well. Okay, so when we're talking about truth-functional completeness, we are sort of making a statement about all possible truth-functional connectives. And just as an example here, we could introduce any number of truth-functional connectives by means of a truth table. And what you're seeing here on the screen is an example of something along those lines. The textbook calls this one club. And it's supposed to model the sort of English sentence, if P, then Q, else R. However, it is a truth-functional connective, and its truth value really only depends on the truth values of P, Q, and R. So the semantics for this particular connective can be completely described using a truth table. Just realize that in this case, we need 8 rows because there are 3 underlying sort of sentences for that connective. In other words, it's a 3-ary connective as opposed to a binary connective like conjunction or disjunction, or a 1-ary connective like negation. Okay. And what you're seeing at the bottom of the screen is a formula in disjunctive normal form. So it's a disjunction of a bunch of conjunctions of literals. And it turns out that if you were to construct the truth table for that sentence down on the bottom, then you would get the same exact column of T's and F's that you see there for this new connective that we just introduced, this club sort of symbol. And what that means is that the two of those sort of statements would be logically equivalent, and not just logically equivalent, but tautologically equivalent. They would have the same sort of values under their main connectives. Now, the thing to recognize is that that statement on the bottom doesn't have any connectives that are sort of strange, like this club or maybe some other strange truth-functional connective that we might be interested in introducing. It just has a conjunction, disjunction, and negations in it. And it turns out that this is always possible. So if you are going to introduce a new truth-functional connective, and it can have whatever arity you would like, just realize that if it has arity n, you're going to need 2 to the n rows in the truth table that introduces the semantics for the connective. But nonetheless, it's always going to be possible to find a formula in disjunctive normal form, like the one sort of down below, or a conjunctive normal form that is equivalent to that truth functional connective that we introduced. And so, in a sense, the conjunction, disjunction, and negation are really all that we needed, right? I mean, we could sort of simulate this strange club connective that I'm talking about. And remember, this is if, then, else via this sort of complex sentence that we see down below. Now, there's a systematic way of constructing that particular sentence down below, and that'll essentially be the proof that conjunction, disjunction, and negation are truth functionally complete. So let's go through the process or that algorithm for taking a new truth functional connective truth table that introduces its semantics and writing down an equivalent DNF and CNF formula. All right, so let's describe the sort of algorithm for constructing a equivalent sentence in DNF form for a given truth functional connective. Now, it'll make a bit more sense when we go through a couple of examples, but here we'll go through this sort of two-step algorithm and sort of outline the details before we try an example. So here we're going to be introducing or supposing that we've been given a new n-ary truth functional connective that we're going to denote by spade, and it has inputs P1 through Pn, and you can assume for the moment that those are essentially atomic sentences. And somebody has also handed you, when they've given you this definition of a truth functional connective, a truth table that tells you the semantics of that particular connective, similar to what we did with club, the three-array connective in our previous slide. And what we would like to do is outline the process for constructing an equivalent sentence in DNF form, disjunctive normal form. Okay, so I'm going to say this and then we'll come back and go through an example. First, for step one, for each row of the truth table, you have to construct a conjunction that encodes the truth values of that particular row. So let's call that C1 conjunction C2 all the way to Cn. And we'll have to do this for every row of the table. And there are, because there are n atomic sentences, 2 to the n rows that we'll have to do this for. Now, in a given row, we'll let Ci be equal to just the atomic sentence Pi if that row marks Pi as T. And we'll let Ci be equal to the negation of Pi if Pi is marked F. So we use sort of the negation to keep track of those atomic sentences that got marked with an F, and we leave sort of the atomic sentence just as itself to mark that it got marked as a T in that particular row. And depending on those negations, this particular conjunction will represent basically the truth value in that row. Okay, now those conjunctions that we created in step one, we're going to form a disjunction of them, but not all of them. We only form the disjunction of all of those conjunctions created in step one from the rows of the truth table that mark our new connective, in this case spade, with a T. So we find those rows that were marked with a T, and we form the disjunction over all of those. And just from the way that we constructed that, that's going to be a disjunction of conjunctions of literals. That's just the process that we followed. And it turns out that the sentence we get is tautologically equivalent to the truth table that we started with. And furthermore, it's in that DNF format. So I haven't really claimed to prove that it's tautologically equivalent, but let's just go through a nice example on the next slide, and hopefully it'll make it apparent why it's sort of tautologically equivalent when you go through this process. And then after we do that, we'll come back and outline the process to find a CNF formula as well. Let's now run the algorithm through our previous example. Here we have that same truth table that we introduced for club. And the first thing that I'll do is actually part of the second step. So I'm going to identify here the various rows of this newly introduced truth functional connective club that are marked with a T. And that's that first row, second row, fifth row, and that second one from the bottom. And they've been marked in green, yellow, pink, and blue. All other rows have an F for this newly introduced connective. And when we form the disjunction in step 2, it's really only over the conjunctions we created for these rows. Okay, so now let's go back to step 1. And remember, in step 1, we actually create these conjunctions for each of the rows. But since these are the only 4 rows that are getting marked with a T, these are the only 4 that we'll have to really write down in our formula. Okay, so let's focus in on that top row up there in green. And notice that in that part of the truth table, P, Q, and R, those atomic sentences, have all been marked with T. And we can encode that information as a conjunction down on the bottom, the conjunction of P, Q, and R. Next, let's move on to the second row. There, the difference is that R has now been marked with an F, and P and Q are still marked with a T. And we encode that with, again, a conjunction, but now we take the conjunction of P, Q, and then the negation of R. And we use that negation to sort of encode the fact that there was an F there in the truth table. Okay, so for that third highlighted row, the one there in pink, P is marked as an F, and Q and R are marked with a T. So we get negation P, conjunction Q, conjunction R. And then finally, that second to the bottom row down there, highlighted in blue, both P and Q were false, and R was marked true. So we get negation P, conjunction, negation Q, conjunction R. And again, the 2 negations there are on the P and the Q because they were marked as false in the table. So those are the conjunctions that we needed from step 1. Now, technically, we should go through and construct them all, but when we write down the disjunction in step 2, these are the only ones we need because these are the ones associated with the rows where our connective was marked as T. So now that we have those connectives, we just form the disjunction of each of them, and that just means putting parentheses around them and adding these disjunction symbols. And there you have a sentence in disjunctive normal form. Let's say a little bit about why it's logically equivalent to the connective that we introduced. For example, let's start with that top row of the truth table. When P, Q, and R are all true, notice that sentence down on the bottom, the only disjunct that will be true is the one in green because P, Q, and R are all true. The yellow one will be false because we have a negation next to the R. The conjunction there in pink will be false because there's a negation next to the P, and the same thing for the one there in blue. So in that top row, the only disjunct among these that is true is the one in green. And that's why it's encoding that particular row. Notice the same thing can be said for the row there in yellow. The only disjunct that'll be true when you plug in, the true and false values into this formula here is going to be that disjunct in yellow because the R will just sort of cancel out with the F to make all 3 conjuncts true. And the conjunction in green, pink, and blue will all be false. So that yellow one will be the only one that's true. But again, because all you require for a disjunction to be true is that one of the disjuncts is true, the whole sentence will be marked as a T. And this is true for all of the highlighted rows that we had. And then to see that the rows that we haven't highlighted result in an F, notice that because of the way those Fs are located, in those rows, they make none of these disjuncts true. So the green, the yellow, the pink, and the blue in those rows are always false. And if you have a bunch of false statements disjuncted together, it still remains false. And so the truth table that you would get would be identical. And it's really just because this disjunctive normal form sentence really sort of encodes the information directly into a sentence constructed from disjunction, conjunction, and negation. We'll also go through another example, getting to a conjunctive normal form, and we'll apply that one to a new conditional connective that we'll introduce as well. So a question that arises often with the previous algorithm is that we just focused on those rows that the connective had a T in. And we sort of got the rows where it had an F for free. But it turns out that we could have focused on the information given by those rows where we got an F and got the information about where it's true for free. And if we do it in that format, we get a sentence that is not in DNF form, but CNF form. Okay, so again, the setup is exactly the same. We have that same spade n-ary truth functional connective that we've introduced with the truth table. Now, in step one, instead of forming a conjunction, we form a disjunction to encode the information in the truth table. But we encode it in the reverse order that we had before. So if a sentence, atomic sentence PI is marked as an F, we now let CI equal PI. Where previously we would have marked it with a negation. And now when CI is equal to the negation of PI, that means that PI had been marked with a T. Okay, so it's basically the opposite of what we were doing in the DNF algorithm. And then now we take the conjunction of all of the disjunctions we created in step two, where we look at rows from the truth table that were marked not with a T like we did last time, but with an F instead. And then you can make sort of the same argument that we sort of made before, that the only way that you're going to get a sort of false statement in this case is if you're in one of these rows and that conjunction was marked as a false statement. So the same sort of argument runs through. And in this case, you have a formula that is now in CNF form. And we'll go through an example of this as well when we introduce the conditional. But really, when we say a bit more about truth functional completeness here in a moment, just one of these algorithms is enough, because it shows that you can express any of these truth functional connectives completely in terms of conjunction, disjunction, and negation. So the main reason for presenting these algorithms was not necessarily to find a sentence in DNF form or CNF form, but instead to prove the following theorem. So we won't give a proof because the proof is essentially the two algorithms that I mentioned before. But let's walk through the statement of it. It says the following: if you are handed an n-ary truth functional connective, say something like spade, and what's meant by that is the semantics for it. So in other words, a truth table with 2 to the n rows. Then there exists a complex sentence in DNF and a complex sentence in CNF that are tautologically equivalent to this n-ary truth functional connective. In other words, every truth functional connective can just be expressed in terms of conjunction, disjunction, and negation. And we'll say that that set of 3 connectives is truth functionally complete. Now, again, the proof of this theorem is just to follow the algorithm that we mentioned before, and you'll produce a sentence either in DNF if you follow the first algorithm, or CNF in the second one. And again, it's not so much that we want that particular sentence, but that it can be done, and that we don't really need to introduce any other new connectives in order to express all of the truth functional sort of expressions that we would like to make. Great. So let's now just be a little bit more precise and introduce a definition. We'll see that a set of connectives, let's call that set X, is truth functionally complete if every other truth functional connective can be expressed with the connectives inside of that set. So just as an example here, we showed in the previous sort of algorithms that the set consisting of the negation, the disjunction, and the conjunction is truth functionally complete. And again, that's that algorithm just either expressing the sentence in DNF or CNF format. And that shows us that whatever truth functional connective we started with, we could just write it down using these three symbols. Now, it turns out that using that piece of information, we can also show that a lot of other collections of truth functional connectives are truth functionally complete. For example, that list of three is a bit redundant. We can either forget about conjunction or disjunction, and we remain truth functionally complete. Now, the way that we would prove, for example, that disjunction and negation, that sort of second one, that second set there, so disjunction and negation is truth functionally complete, is to recognize that a conjunction like P and Q can just be replaced by De Morgan's law with something like the negation of P or the negation of Q. And again, those two things are equivalent, tautologically equivalent to one another via basically something along the lines of De Morgan's law, or you can just check with the truth table. And so when we put a sentence into disjunctive normal form, we can take any of those sort of conjunctions that we had and just replace them with these extra negations, these three extra negations in a disjunction. And that'll remove the conjunction from any of our symbols. And the same thing is true of disjunction. So that third line down, if we take conjunction and negation, that's also truth functionally complete. And that's because the disjunction, any disjunction that you write down can just be rewritten in terms of three negations. So the negation of the negation P, conjunction, negation Q. And that expression that you're seeing only involves negations and conjunctions. So basically, you would write something down in conjunctive normal form, and then those disjuncts that you had of literals, you could just sort of rewrite using this format. And so here we have a nice example of three collections of connectives that are truth functionally complete. And there are lots of other ones. And in fact, it turns out that there are some connectives that are just on their own truth functionally complete. So on the next slide, we'll visit an interesting truth functional connective that we haven't seen yet. And we'll only visit it because of the novelty of the fact that it on its own is truth functionally complete. So let's look at a good example of another connective that turns out to be truth functionally complete all on its own. This connective is called the Sheffer stroke, and it's denoted just with a vertical bar. So you put the sentence P, a vertical bar, and then Q. The English translation, there are sort of two of them. You can think about it as the statement neither P nor Q, or sometimes we'll say not both P and Q. So not both P and Q. And the truth table sort of indicates that. You can see it up there in the upper right-hand corner, and it's the complete semantics for this truth functional connective. The only time that this Sheffer stroke is marked with an F is if both P and Q are true, right? Because again, I was saying it's not both P and Q. So if both of them are true, it should be marked as false. And then in all other cases, it's marked with a T. So that's sort of the semantics of this new connective. And what I would like to prove for you is that this connective on its own is truth functionally complete. The proof relies on the fact that the disjunction in negation, that pair, is truth functionally complete on their own. And we saw that by first sort of applying the algorithm and constructing something in disjunctive or conjunctive normal form, and then replacing all of the conjunctions with something along the lines of De Morgan's law. Okay, so what that means is that any truth functional connective can be expressed in terms of disjunction and negation. So let's assume that we have some expression in that form. Then what we can do is we can replace all of the instances of the negation of P with the expression P stroke P. And the reason why is that if you construct the truth table for P stroke P, it is exactly the same as the truth table for negation P. In other words, they're tautologically equivalent to one another. So everywhere in the sentence that we saw a negation of a sentence, we could have just replaced it with that sentence stroke with itself. And then the same is true of the disjunction P or Q can be replaced with this sort of complex sentence down here on the bottom where we have P stroke P stroked with Q stroke Q. And that sort of basically undoes the negations and gets you back to an or. And that means any disjunctions that we see in our sentence can then be replaced with these three strokes. And what will result is a tautologically equivalent sentence with nothing but strokes in it, meaning that this connective on its own is truth functionally complete. Now, this is similar to exercise 7.29 in the homework assignment. And in particular, there you're asked to do exactly this, prove that this Sheffer stroke is truth functionally complete. And the proof is basically done for you here, but what I would like to see in your proof is the truth tables for P stroke P and P stroke P stroked with Q stroke Q, verifying that they are tautologically equivalent to the negation of P and P or Q, because that's the only piece that would be missing here from a proof that, or a complete proof that this connective is truth functionally complete. Let's change gears a little bit and introduce a new, interesting binary truth functional connective. It goes by the name of the material conditional, and it is the conditional that is used in mathematics all over the place. And in terms of its English language translation, the conditional is the if P then Q statement. And here it's just a truth functional statement when we say the material conditional. Sometimes this can be a bit confusing for students, and the book does an excellent job of talking about how in sort of regular everyday English, the conditional can sometimes be problematic and convey more information than just what's shown in a truth functional sort of setting. And so this sometimes is confusing for students. However, we'll focus mainly on the material conditional, and the material conditional is just truth functional in nature, just like the conjunction or the disjunction. And we introduce the semantics for this particular connective with the truth table below. In this case, the conditional has two atomic sentences, P and Q, sort of as its inputs. And the only time that we get an F marked for our conditional is when P is true and Q is false. In all other instances, our truth table is marked as a T. Now, as we said previously, the disjunction and negation are truth functionally complete. So this connective, the conditional, can be rewritten in terms of the negation and the disjunction. And it's pretty straightforward to see how to do that. If you follow our second algorithm, turning this new connective that we constructed into an equivalent sentence in conjunctive normal form, then all you would do is focus on that second line, because that's the only place where this particular connective is marked with an F. And then you would encode that row, the truth values, in a disjunction. The P is marked as a T, so you encode that with the negation of P. And the Q is marked with F, so you encode that with just a Q. And then you would form the disjunct, and that's what you're seeing at the top, the negation of P, disjunction Q. And so that's the sentence we would get in CNF form from following our algorithm, and it's equivalent to our conditional. In fact, we could have just defined the conditional to be shorthand for this particular sentence in our language. Nonetheless, this conditional will be fairly useful, and we'd also like to add it to our deductive system. So we would like to reason with it in our formal proofs. So we'll say a bit more about that. But on the next slide, I'd like to say a bit about how conditionals are stated in English, because there are lots of different variants and forms and ways of stating a statement like if P then Q. So here are just a few of the ways that the English language allows one to represent a conditional, and in particular for us, the material conditional. So that would be this P arrows Q. Probably the most standard way is to say something like if P then Q. Another way to say the same sentence is to say P only if Q. You can sort of form a converse of this, sort of flipping the order of Q and P in your sentence, if you use the construct if instead of only if. So here you would say something like Q if P. And then you can also use the word provided. So sometimes they'll say provided P, Q, or Q provided P. In each one of those cases, you'll translate that English sentence as the material conditional P arrows Q. It's often the case as well that the sentence negation P arrows Q, or sort of a conditional where that first sort of sentence has a negation on it, happens often and throughout mathematics. And it happens so often that there are some nice sort of phrases to indicate. The first is to say something along the lines of Q if not P. So the if not is this negation of P arrows Q. And that is intended to line up with the notation that we use above for Q if P. So notice that we just put the not right next to the P here. But often in English, you'll hear sort of a sentence, Q, and then if not, a sentence P. And what's meant by that is, again, this conditional statement. In mathematics, we often use the word unless, and when we say Q unless P, again, what we mean is that the negation of P arrows Q here, right? So if P is not true, then Q is true. And finally, you can also sort of move the P out to the front and say something along the lines of unless P, Q. And again, each one of those just sort of is a way of indicating that that P in the front of the conditional there has been negated. Now, this is also good to point out that these various variants of the conditional are really helpful in writing informal proofs as well, and just giving you some different ways of saying the same sort of thing so that your sentences aren't always if then, if then, if then, if then, and things like that, right? So that can get sort of dry pretty quickly. And this allows you to sort of change up the phrasing a little bit and make it a little bit easier to sort of read through a proof. But that's mainly style. That's not something that you'll be graded on or anything along those lines. But just realize that when you see these sort of phrases in mathematics or just in English in general, they are relating back to the conditional. So one of the main reasons we introduced the conditional into our first order language is to capture the notion of tautological consequence and logical consequence within a formalized complex sentence. So for example, if we focus in on this first if and only if statement, Q turns out to be a tautological consequence of P1 through Pn if and only if the conjunction of P1 through Pn sort of arrows Q. And here by arrow, we mean that conditional connective. If that conditional is actually a tautology. Remember, tautology just means that underneath that main connective, you've got all T's. So we can check a tautological consequence not by having to go through the entire table and looking for all the places where P1 through Pn are true and then checking to see if Q is true, but instead just looking at the truth values of this single sentence. And the same thing is true for logical consequence, except for we replace the notion of tautology with logical truth. So that conditional statement with P1 through Pn and Q, if that's a logical truth, then we have a logical consequence. Now, the proof is not too bad and fairly straightforward. Let's first suppose that P1 through Pn arrows Q is not a tautology, right? So what happens in the case that that conditional statement is not a tautology? Well, if it wasn't a tautology, there would be some place where it got marked with an F in our truth table. And the only way a conditional can be marked with an F, if we think back to the way we introduced it, is if that conjunction of P1 through Pn is true and the Q is marked as false. Now, the only way a conjunction is going to be marked as true is if all of the conjuncts are true. So P1 through Pn. So here we would have somewhere in the truth table where P1 through Pn are all marked as true, but Q is being marked as F. And that would tell us that we would not have a tautological consequence. And vice versa, if we actually did have a tautological consequence for the very same reasons, when we look at that rows or the rows of the conditional statement, they would all have to come out as true, because either the conjunction here, P1 through Pn, would be false, meaning the conditional statement would be true, or if P1 through Pn are all true, then Q would have to be true and the conditional would be true. So here we have this sort of if and only if based on the tautology. And the same sort of argument works in the case of logical consequence, replacing tautology with logical truth. It'll also be convenient for us to introduce the biconditional. And the biconditional will use the double arrow for our symbol. It is a binary truth functional connective. And the semantics are given by the table at the bottom. It gets marked with a T, provided that P and Q have the same truth value. And it gets marked with an F if they have different truth values. It also turns out that it's logically or tautologically equivalent to a statement that can be made in terms of a conjunction and the regular material conditional. And that statement is written here on the top. And that tautological equivalence can just be checked by constructing a truth table. Now, the reason why I've included it here on the top is it helps us a bit with understanding where the translation comes from, where the English translation for the biconditional comes from. So that first conditional on the top, we've got P only if Q. So the first conditional up there, P arrows Q, is P only if Q. And then we've got a conjunction, and then we have Q arrows P. So it's written in the reverse order. And now that's the same thing as saying P if Q. So Q arrows P is P if Q. And P arrows Q, that first one, is P only if Q. And we often abbreviate sort of the conjunction by just saying them together. So we'll often read off this biconditional arrow as something like P if and only if Q. And often in mathematics, we'll also abbreviate that even further to just IFF, if and only if. Just like the conditional allowed us to encode logical and tautological consequence, the biconditional allows us to encode logical equivalence and tautological equivalence. And it turns out that two sentences P and Q are tautologically equivalent if the complex sentence formed by P biconditional Q, that double arrow in between P and Q, turns out to be a tautology. So again, we can check tautological equivalence not by having to go through the whole table and check to see that they have the same columns, but instead just by looking to see if this biconditional statement is a tautology. And likewise, the notion of being logically equivalent is the same as the biconditional being a logical truth. And so again, this is one of the reasons why we introduced this into our logical system. Okay, so now that we've introduced these symbols for the conditional and the biconditional into our system, we would not only like to understand their semantics, but also their syntax. And that means we would like to be able to reason about them within our formal proofs. Now, that requires us to then have some sort of elimination and introduction rules for the conditional and the biconditional. But fortunately, they're among the most intuitive of the rules that we see, and they'll help us as we construct our formal proofs in the sense that it'll more easily allow us to mirror our sort of informal reasoning about these formal proofs. Okay, so let's focus first on conditional elimination. And let me just remark that in italics down there, I've called this particular rule modus ponens because it's a classical rule of logic, and it's been studied all the way back to the Greeks and the time of Aristotle. So it goes by this Latin name of modus ponens, but we'll call it conditional elimination when we're citing it in our formal proofs. Now, what it says is that if you've proven the conditional P arrows Q, so P implies Q, and you've also proven that P is true, then later on in your proof, you can cite those two sentences and conclude that Q must also be true as well. So if P implies Q and P is true, Q must be true as well. And again, here we would have to go back whenever we're using this conditional elimination and cite these two particular sentences. And again, it's an elimination rule because notice that we go from lines that have a conditional to lines that don't. Conditional introduction is essentially exactly the way that you would go about proving a conditional statement. So if you are tasked in a mathematics course to prove a conditional statement like if P then Q, what you immediately do is you assume that P is true, even if you don't know it's true or not. You assume that P is true, and you argue step by step that Q has to be true. And once you arrive at Q, you finish your proof and say, okay, the conditional statement had to be true. And we have a nice way of introducing temporary assumptions within our Fitch style system. That's with a subproof. So conditional introduction starts by introducing a subproof with the temporary assumption that P is true. And then if you can reason down to another statement Q, you can then discharge the subproof, end the subproof, and discharge that assumption of P, and conclude outside of the subproof that the conditional P arrows Q is true. And you would have to cite that entire subproof that you had above. But again, that's just exactly the way you would go about proving a conditional statement. You assume that P is true, and you reason to show that Q has to be true as well. We'll also need some rules for reasoning about biconditionals, and they're almost sort of identical to those for the conditional, just meaning you have to sort of go in both directions. So first off, let's focus on biconditional elimination. And let's suppose that at some point in your proof, you've shown or you've proven that P biconditional Q is true, right? So this double arrow between P and Q is true. And then later on down the line in your proof, you also sort of conclude that P is true. Then you're free on a line further down below those two by citing those two and biconditional elimination to conclude that Q had to be true. And it makes sense. I mean, P and Q, this is the same thing as them being sort of logic. Like the only reason those would be true is if they're logically equivalent. And so if P is true, you can be assured that Q had to be true as well. Okay, so that's biconditional elimination. And notice that the order of P and Q doesn't really matter, right? So just like when we're using equality elimination, it doesn't matter the order of the two sentences. Okay, so what about biconditional introduction? How do we introduce a biconditional? Well, basically, we just prove that P implies Q and Q implies P. So we assume P and show that Q is true, and then we assume Q and show that P is true. And we think about it really as like cases, right? It's a two-case proof here. You assume that P is true and get to Q, and then case two, you assume Q is true and then get to P. And if both of those are true, you can cite those two subproofs and conclude the biconditional, that P and Q are essentially logically equivalent to one another. Okay, so really, again, we could get around using any biconditionals by just sort of using the rules for conditionals. But here, it'll just make some of our arguments in our formal proofs a little more sort of matched up with our informal reasoning. So they're more a matter of convenience rather than a necessity. So the last sections of chapter 8 go over the proof of the soundness theorem. And as I said at the start of the video, I'll wait until our next module to prove the soundness theorem. And then it completely avoids the proof of the completeness theorem. But nonetheless, we will sort of skip to the more advanced sections of the textbook and go through the proof of the completeness theorem sort of next week. And that'll finish up basically our first part of the textbook. And that's the part about propositional logic. Propositional logic being sort of zero order logic where there are no quantifiers at all. And we will then move on to true first order logic, where we start introducing variables and quantifiers like the universal quantifier and the existential quantifier. But next week, we'll mainly focus on those two proofs, the soundness and the completeness proofs. So let's just say a little bit, or let's look forward to what we're going to be doing, or what we're going to try and prove sort of next module. So the first bullet here is known as the soundness theorem, and the second bullet is known as the completeness theorem. Now, the soundness theorem says the following. If S turns out to not be a tautological consequence of P1 through Pn, in other words, there's somewhere in the joint truth table that makes P1 through Pn true and S false, then there will be no proof of that statement from those premises P1 through Pn that uses just the introduction and elimination rules for negation, disjunction, conjunction, the conditional, the biconditional, and the contradiction symbol. And we'll actually prove this via what's called the contrapositive. We'll show that, in fact, if there is a proof of S from the premises P1 through Pn using this Fitch system, using our sort of methods, then S will have to be a tautological consequence of P1 through Pn. And that'll require us to sort of analyze rule by rule and so on and so forth. So that'll be the soundness theorem. And the far more interesting theorem, and the one that will require quite a bit more depth in terms of the proof, and the book actually avoids it here in chapter 8 and waits to a later section, is the completeness theorem. And it says the following. If you have a tautological consequence, so if you know that anywhere where P1 through Pn are marked with a T in a truth table, then S is also marked with a T. In other words, S is a tautological consequence of P1 through Pn. Then you can be sure that there is a proof of S from the premises P1 through Pn using only the introduction and elimination rules for negation, disjunction, conjunction, the conditional, the biconditional, and the contradiction symbol. Okay, and again, it's sort of a detailed proof, so it'll take most of the video for our next module.